Hello viewers, welcome to CEC Gurukul lectures. In this series on stereoisomerism, I have discussed geometrical isomerism with you in great details, where I had discussed geometrical isomerism of alkenes and cycloalkanes. We have also discussed the EZ notations there for assigning configuration to alkenes. Today we shall be starting with another type of stereoisomerism, which is optical isomerism. So optical isomers are stereoisomers that interact with plane polarized light, and they have the ability to change the plane of plane polarized light. Such compounds which can change the path of plane polarized light are known as optical isomers. These compounds have similar physical and chemical properties, but they differ only in their behavior towards polarized lights and are called optical isomers, and the phenomena in which they change the path of plane polarized light is known as optical isomerism. So optical isomerism, please remember, optical activity of a molecule is a physical property. And before we proceed further as to what are optical isomers, what is optical activity, let us see what is a plane polarized light, how is it related to normal light, and what do we mean when we say that optical isomers will change the path of plane polarized light. When we talk of an ordinary light, it consists of electromagnetic waves which oscillate in all directions, which is perpendicular to the path of propagation. So we say that light waves which oscillate in all directions are said to be unpolarized, whereas plane polarized light oscillates in single plane which is perpendicular to its path of propagation. And how do we get this plane polarized light? When we pass an ordinary light, that is monochromatic light, through a polarizer, which we can here use as a Nicol prism, which is made of calcium carbonate, that is calcite, then this polarizer will convert normal light into a plane polarized light, and the light which comes out of Nicol prism is the one in which the particles or light is vibrating only in one plane, and this is known as plane polarized light. So what is a Nicol prism? A Nicol prism is made up of two prisms of calcite, that is calcium carbonate, held together with a thin film of Canada balsam, which is a transparent liquid having a refractive index of 1.4865. So here I have shown as to how we are going to get a plane polarized light. We have a light source, and normally we take a monochromatic light. So here we have taken a sodium lamp, and when this monochromatic light comes out of the sodium lamp, its waves are oscillating in all directions. And when we pass this light through a polarizer, which can be a Nicol prism, what happens here, that now the light coming after passing through Nicol prism, the particles start vibrating or oscillating, the waves start oscillating only in one direction, which is perpendicular to the path of propagation. Like this is the path of propagation, and these waves are oscillating in a direction which is perpendicular to path of propagation, and this light is now known as plane polarized light. So what is the difference between an ordinary light and a plane polarized light? In ordinary light, the waves are oscillating in all directions which are perpendicular to the propagation of light, whereas in plane polarized light waves are oscillating in only one direction, which is perpendicular to the path of propagation. So as I've said, that light waves which vibrate only in one direction are called plane polarized light, and the phenomena by which we are converting normal light into plane polarized light is known as polarization. So when we pass this monochromatic light through a polarizer, what happens? Its oscillations in all the directions are blocked except one, and when we find that this light is now oscillating only in, the waves are oscillating only in one direction. So what we find now, what is the relationship between an optically active compound and plane polarized light? We find that some compounds have the ability to rotate the plane of polarized light passing through them. That is, when we pass this plane polarized light through a solution of a certain compound, and if it is optically active, it will change the path of polarized light. And if it is able to change the path of plane polarized light, we say that that compound is optically active. And the property is called optical activity. The angle by which the plane is rotated is known as optical rotation. Right? So now, what does this angle of rotation depend on? So rotation in angle of plane polarized light occurs because there is interaction between the electric field of light beam and moving electrons, and the light is diverted from its path. Now we say a compound that rotates the plane of polarized light in clockwise direction or right direction is known as dextrorotatory, and a compound that rotates the plane of polarized light in left or anti-clockwise direction is known as levorotatory. So dextro word is obtained from a Latin word dexter, which means right, and a dextrorotatory compound is indicated by notation plus or small d. Please remember small d. Whereas when we talk of levorotatory compound, here levo comes from the Latin word levus, which means left. So in this case, that means the compound is rotating the plane of plane polarized light in left hand direction, which is indicated by minus or small l. So this small l and small d are old methods of giving notations to dextrorotatory and levorotatory compounds. And please remember, when we are referring to optical activity, we will refer it by small d and small l. Later on, we shall be using notations D, capital D and capital L. There I will tell you what is the difference between small d and small l. They are entirely different notations. So please remember, small d and small l refers to optical activity. That is the old method, but we can still use it. And the new method of notations for indicating a dextrorotatory compound and levorotatory compound are plus and minus. So what happens when we pass a plane polarized light through a compound? So again, I have already told you how will we get a plane polarized light. We have sodium source here. The waves are oscillating in all directions. We pass these rays through Nicolin prism which is a polarizer. This is fixed, and then it will, these particles, the waves will now start oscillating only in one direction, which is perpendicular to the path of propagation. Now what we do, we take a solution of the compound, or we can take the pure compound, which is transparent liquid, and we put it in this tube which is holding the sample. When the plane polarized light passes through it, it will interact with the compound which we have taken in this tube. If this compound is optically active, it will change the path of plane polarized light, and then this compound is said to be optically active or chiral compound. These terms I will be introducing in my next lecture as to what we mean by a chiral compound. Now, but in second case, we've kept everything same. We have changed the compound here, and what we find that there is no effect on the path of plane polarized light. It is same before passing through the sample as well as after coming out of the sample. So we say that this compound is optically inactive because it did not change the path of plane polarized light. Now this optically active compound may be optically active as such, or it may be a racemic mixture. Again, we will be introducing the terms racemic mixture in the next class, which I'll explain there. And now the magnitude of direction of optical rotation produced by an optically active compound can be measured by an instrument known as polarimeter. The simplest polarimeter is composed of a light source, which I have already said is usually a sodium lamp. We have a polarizer. What does a polarizer do? As now you are very much familiar with it. It will convert a beam of light of mixed polarization into a beam with well-defined polarization. So here we are passing it through Nicol prism. We are using that as a polarizer. Then we have a tube which is holding the sample. We have an analyzer which is again a Nicol prism, and this will show us what is the change in rotation. And now we have to measure what is the change in rotation of plane polarized light. That we will measure with a measuring scale. It will help us in determining, that is, what is the change in number of degrees of rotation. So here on your screens you can see a polarimeter. Here we have a sodium source, then we have a Nicol prism, the polarizer. This is fixed. Rays are passing through it. It becomes the normal light from unpolarized to polarized. Now this polarized light the electric field of this polarized light will interact with the moving electrons of the molecule, and it will change, the compound will change the path of plane polarized light. So what we find that the light which is coming here, its direction of rotation is different as compared to the light which was entering the sample tube. So that means this compound is optically active since it has brought the change in the path of plane polarized light. This will be now analyzed by the analyzer, which is a fixed Nicol prism, and we can read the reading here on the scale, which will show what is the change in angle of rotation. So that means now what will the angle of rotation depend on? It will depend on the following factors, which are the nature of the substance, whether the substance is dextrorotatory or levorotatory. If it is dextrorotatory, the light will be rotated in the right hand direction. Then it will depend on the wavelength of the light used, and here we are using sodium source, so the wavelength here would be 589 nanometers. Then the concentration of the solution will be taken in grams per ml. We will use a solvent. If our liquid, our optically active compound, or the compound which we are analyzing is a liquid, we will just take pure liquid here and we will make its concentration in grams per ml. We will measure its concentration. Whereas if it is a solid, we will make a solution in a solvent. So what should be the nature of solvent be? Solvent should be inert, that is, it should not react with the molecule, and second, it should itself not show optical activity, that is, it should not react with plane polarized light. If it does show, it will affect the overall angle of rotation of the plane polarized light. So we have to keep a inert solvent here. Then the length of the path, that is length of the tube, will also make a difference. And we take the tube, the path is measured in decimeters. And then of course the experimental temperature. So now we say what is the rotation produced by a typical sample. So we say the number of degrees that a plane of polarized light is rotated as the light passes through a solution of optical isomers depends on the number of chiral molecules in the sample. So that means it will depend on the concentration of the sample. And you know what will the concentration of sample depend on? It will depend on the length of the tube, and it will depend on the concentration of the optically active isomers, that is the enantiomers. So now if we have to obtain specific rotation, now you know that alpha indicates the angle of rotation. Now we have to measure the specific rotation, and please remember every compound will have its own specific rotation. That is, if I say that one compound A is having specific rotation 56, then one of the isomers will be dextrorotatory, whereas the other isomer will be levorotatory. And now I compare it with optical rotation of another compound, which is say B. So the optical rotations of these two compounds will be different, and they will be specific to a particular compound. So how do we find out the specific rotation? So as I've told you that this alpha is the observed angle of rotation. This may be clockwise or anti-clockwise. Then we have the length of the tube, and this is measured in decimeters. We have the concentration, and please remember concentration will be measured in grams per ml. And then this is specific rotation. So this observed rotation, when we put it in a square bracket, it indicates it is specific rotation. This is the temperature, which will be constant, and the wavelength is also constant. So this we've observed. These two also we are getting from our experiment, that what is the concentration we are using of the sample, that is what is the length of the sample tube, and what is the concentration of the substance. All these three are known. So from this we will now calculate the specific rotation. Here I have, so that means how will we now define specific rotation? So when we are going to compare the specific rotation of two compounds, irrespective of what concentration we've taken in the beginning, we will convert that into 1 gram per ml, and the length of the tube will be considered as 1 decimeters. So let us now define specific rotation. Specific rotation is defined as the rotation in degrees brought about by a pure transparent liquid or a solution containing 1 gram of optically active substance per ml of solution placed in 1 decimeter of polarimeter tube. So that means when we are comparing specific rotation of two compounds, the concentration would be same, the length of the path will be same, wavelength will be same, the temperature will be same, and what we'll get, but the angle of rotation in each case will be different, and from there we will be able to find out what is the specific rotation of that particular compound. So I have given, let's do a numerical, simple numerical, to see whether we've understood this concept or not. That is, determine specific rotation of 2-butanol, which when placed in polarimeter gave an observed rotation of 4.05 degrees counterclockwise. So when we say counterclockwise, it means that it is anti-clockwise. So from here we can conclude that this 2-butanol is levorotatory. Now we have to convert this concentration in what is the concentration per ml. So what are we doing? We have taken the solution and we have prepared the solution by diluting 6 grams of 2-butanol to a total volume of 40 ml. So we will now find out the concentration by dividing 60 by 40. That will give us the concentration in 1 ml. And now we have this in millimeters. So what we'll do, we will convert millimeters into decimeters, and we know 200 millimeters is equal to 2 decimeters, and here we have found out the concentration, and we get the concentration here is now 0.15 grams per ml. Here the length of the tube is 2. When we divide the observed rotation by the concentration of the compound, we get a value of minus 13.5 degrees. That means that 2-butanol is levorotatory, since it was rotating the path of plane polarized light in left hand direction, and the specific rotation of 2-butanol is 13.5 degrees. So what we've discussed till now is that some compounds have the property to rotate the path of plane polarized light. So what are these compounds, or what is the property which is in these compounds which will make them rotate the path of plane polarized light? For this we shall be discussing the history of optical activity in brief. So in 1813, French physicist Biot, he found out that some inorganic compounds like quartz, crystals of potassium chlorate, potassium bromate, and sodium periodate were able to show optical activity in crystalline structure. How did he come to conclusion that these inorganic molecules were showing optical activity in crystalline structure only? Because what he did in his experiment, he ground the substance, he fused the substance, and then he dissolved the substance in a solvent. And what he found, that when he did this, the crystalline structure of the inorganic substance was destroyed. That is, the crystalline structure of quartz was destroyed. That means if there was something, that is, the asymmetry which was in the molecule was destroyed, and this was not able to show optical isomerism. So I shall be discussing as to why organic compounds show optical activity in my next class. Thank you.